allow me to recapitulate. Looking at the triangle, I have talked about very classical features, promising you that I would round off my talk by delineating what people like to call the 4 remarkable points. Okay, so of these 4 remarkable points, we have done 3. The one was the circumcenter, the center of the circle that goes through 3 vertices of the given triangle. That was denoted by O, it was called the circumcenter. And closely related to it, the ortho center, the point in which the 3 altitudes concur. 3 altitudes intersect in the same point, and it's denoted traditionally by H and traditionally referred to as the ortho center. And finally, the 3rd remarkable point was the centroid, which was the point in which the 3 medians concur. A median being, for instance, a median through the vertex A being the straight line joining A to the midpoint of the line segment BC, midpoint of the opposite line segment. Okay, so, and we pointed out that these 3 points were quite well known to all sorts of various diverse civilizations, and for a very long time. It was, however, Leonhard Euler who noticed that, in fact, these 3 points lie on a straight line and have a very remarkable, and they divide one another in a rather remarkable ratio. So, I would like to make this precise by presenting it in the form of a theorem. But if you like, let me entitle my talk Euler. So what Euler notices. By the way, it's Leonhard Euler. Dates are okay. Leonhard Euler. Well, he has noticed 2 things. One, let me write it in form A, that the points G, the points L, H, G, these 3 points are collinear, besides collinear, and they've got this very peculiar relationship that the ratio of GL to GH is in fact exactly -1/2. So I mean, if you want a picture, these 3 points have constitute a configuration like this. This is H, this is O, and G is okay. So if you divide this line segment into 3 equal parts, it's how interesting. This is 1, this is 2. And O and H are on the opposite sides of G. So that's, and this line is referred to as the Euler line, so on and so forth. Yet, this was not all. The history is a little complicated. But there is also a second part which is attributed to Euler and perhaps another person. Let me note his name. Carl. This is a name to be noted. Carl Wilhelm Feuerbach. It's not a philosopher Feuerbach. That's someone else. And in fact, he has lived very short, briefly, unfortunately, 800 to 834. Little is known about him, and apparently he is co-discoverer of math in this configuration. But anyhow, what comes next is the following. Euler notices Euler and Feuerbach, of course, the midpoints of the line segment BC. Okay, so the three sides, BC, CA, AB. So observe 3 points. Okay, so and the midpoints of not the sides but those line segments joining the awful center to the 3 vertices. Let's say HA, HB, and HC. Well, already I got a considerable list. And the feet. The feet of the altitudes line and circle are concentric. That's to say, there is a unique circle containing all these points. Let me point out, we have already seen, that was the very first theorem which we'll look at. If I give you 3 points, if they're not collinear, then you can draw a circle through them. In fact, a unique circle, that's the circle of the triangle. So there is nothing quite extraordinary about 3 points lying on a circle. Yet, I think a mathematician or a geometer worthy of the name should sit up and take notice if 4 points lie on a circle. It would be even more remarkable if 5 points, 6 points lie on a circle. Observe, in this case, we have got 9 points sitting on a circle. That's something quite Euler, I should say. Okay, so in fact, this circle is referred to as the Euler circle or the 9-point circle. There are all sorts of names. Some people would like to call it the Feuerbach circle. Anyhow, 9-point circle, I think, is quite neutral and matter of fact, so that's okay. In fact, there is one more thing to notice. So these points lie on a circle. Okay, so let me do it like this. Lie on a circle. Let me do it like this. Not arc-concyclic. Obtuse lie on a circle. Lie on a circle. Circle. Where off the center? The center is the midpoint of of LH. Okay, so let me draw a picture beforehand. So you have got this curious line, remarkable line segment. Okay, that's O, the circumcenter. That's H, the alpha center. Here, 1/3 of this interval, you've got G, and right in the middle, it's a point E, central to 9-point circle. Okay, so that's the center I shall denote by E. I mean, you referring to that anyhow. So it's interesting to notice that if this is 1 unit length, then the geo line segment geo is 2 unit lengths, and of course this is 3 units length. So that is that's a quite a remarkable configuration itself, along the line containing these points. Okay, so how to prove this result? Okay, so this is so why this circle happens? Okay, of course. Okay, so let me start by drawing the triangle. It is rather difficult to get these configurations right. I mean, you will get them right, but in my opinion, there's a certain type of configuration which is appropriate for, how should I say, it somehow has this property of being optically pleasing and somehow aiding the learner's memory. Okay, so let's start with this triangle. Okay, so what does the theorem say? The theorem says that the midpoints of the 3 sides, so I will take the midpoint of BC, midpoints, I have made a habit of referring to as A prime. Midpoint. Okay, so let me go on cyclically. So the midpoint of CA is B prime, and the midpoint of AB is C prime. Okay, so there I am. Okay, so these are the things. And then he says, let's look at the altitudes, the three altitudes. Okay, so I'm being careful because, you know, when you are sitting so close to the picture, you tend to lose your sense of proportion and you make really funny pictures. Okay, so that's there. And the third altitude here. Okay, so there we are. And I have made a habit of referring to the feet of the altitudes as A tilde, the feet of altitude through A. Similarly, B tilde. Okay, so you know that's a very good idea. Making a habit of choosing your notation in this cyclic fashion. Okay, so of course this is the point H, your orthocenter. So what the theorem says is that I shall take, the theorem says that the midpoints of the sides and the midpoints of the line segments joining the orthocenter to the three vertices. Okay, for instance, H, the orthocenter, let's join to A and let me take the midpoint and let me call this K. Well, let me take the midpoint of HB, let me call it L. There we are. And HC, midpoint of it, I have to be careful about that. Yeah. Here we are. M. Okay. So, Hamilton, you've got your 9 points, and all these 9 points lie on a circle. Well, how to prove that? That's not too difficult. In fact, okay. So for instance, oh, by the way, okay, so let me make life easier for you. And let me tell you, right at the beginning there, this circle will admit the line segment KA prime as its diameter. Okay? So, you know, I'm making life easier for you. So, well, you will get on. So what you have to do is to show that, okay, so K and A prime as extreme points of the diameter, they are already on the circle. So we have taken care of 2 points. So you've got still 7 points to go. Okay. So how about this? How do you take care of B prime, for instance? Well, that's very easy, because you see, KB prime. Let's look at this. KB prime, and think about our wise man, one of the wise men, Thales. You see, K is the midpoint of AH, B prime is the midpoint of AC. So it means that if you take the line KB prime, it will be parallel to HC. So you notice that KB prime is parallel to HC. And then you notice that if you take A prime, B prime, well, A prime is the midpoint of BC, B prime is the midpoint of AC. So it means that B prime, A prime is parallel to AB, where BA. Well, that tells us, okay, so on the other hand, notice that CH is in fact the altitude through C. So you know that HC is perpendicular to BA. Well, that tells us that KB prime, this tells me that KB prime is perpendicular to A prime, B prime. So, done, you're finished. So you have shown that, in fact, this angle is a right angle. So B prime is indeed on the circle of diameter K A prime. You have done it. Now let's look at, do I have to, I think it would be insulting your intelligence to say that, to go through the very same proof with C prime. Okay, Similarly, if you take KC prime, joining midpoints of AH and AL, if you look at C prime, A prime, which joins midpoint of AB to midpoint of BC, well, these are perpendicular to orthogonal to. So let me make a list of midpoints that are taken care of. Look here, K and A prime. Well, they are taken care of because they are the extremities of the diameters. They are taken care of. I have also taken care of B prime. I have taken care of C prime. So, I'm making good progress. How about M? Well, M is simple too. So, if I join K and M, okay, observe that K is, once again, the midpoint of AH. M is midpoint of HC. Look here. Midpoint of M, midpoint of HC, K, midpoint of HA. What does Thales tell me? Thales tells me that MK must be parallel. Okay, so similar. Okay, so this is finished. Now so I've got MK parallel to CA, excellent. And then how about MA prime? This is not very good. This is not very good. So let me do something like this. Okay. You know, this drawing is not easy on the blackboard. Okay, right. Anyhow, so MA prime. M is the midpoint of HC. A prime is the midpoint of BC. So MA prime is parallel to MA prime is parallel to HB. But you see, HB is in fact the altitude through B. So HB is perpendicular to CA. So they've got finally HB perpendicular to CA. So combining all these, you come to the conclusion that the line MK must be perpendicular to the line MA prime. So you've done it again. You have done it again. That this angle is 90 degrees. So that I think it would be really insulting your intelligence if I say that if I repeat the argument for the point L. Okay, because it's exactly the same thing. L is midpoint of PH, K is midpoint of AH, so LK is parallel to AB, whereas A prime is midpoint of BC, L is midpoint of LH, so if you join them, LA prime is parallel to HC, which is the altitude through C, so CH is perpendicular to AB, hence KL is perpendicular. So you have proven that in fact this is 90 degrees too. So I've got M and L. So L and M. Well, I'm almost complete. I've already got how many points? KL, M, A prime, B prime, C prime, prime. Okay. Now there's an easy one. So there's a very easy one. So Ka prime, we want it to be the parameter, and we want the fruit of the altitude A tilde to lie on the circle which admits Ka prime as its diameter. But that's trivial. This angle is 90 degrees, isn't it? So I have already taken care of A tilde. So I'm left. The only points that are left for me to take care of are the feet B tilde and C tilde. Let me do B tilde. Perhaps I should convert these lines into dotted lines, perhaps. Right. So that's. Okay. Now how about B tilde? Now I have to prove that the angle KB tilde. So So I have to prove that actually the line segment Ka prime subtends a right angle at B tilde. How are you going to do it? Now that's somewhat problematic, but remember this. If you get a right triangle, any right triangle in fact, and if you take the midpoint of the hypotenuse, if you join it to the vertex where the right angle is, then these three straight lines, these three line segments are equal. In particular, this is an isosceles triangle, and the angle, this very narrow, this angle which I have depicted as a very narrow one, is equal to this one. So let's say 1 is equal to 2. Now, you see, the crucial thing is that this is 90 degrees, because B tilde is the foot of the perpendicular from the foot of the orthogone dropped from B onto CA. That's good. So it means that B tilde B C. So let's assume I'm talking about B tilde B C. Oh, I'm sorry. That's everything. B. Okay, so B tilde C is an isosceles, is a right angle triangle. And A prime is the very midpoint of BC. So it means that this 1 is equal to 2. What's 1, what's 2? Well, this is 1. This is 2. These are equal. Fine. So, how about this? With this, I'm looking at a different right triangle. Let me look at the right triangle this time, so I'm changing the right triangle. The very same observation, in fact. Again, I choose this as B. I choose this as B tilde. Then I look at the triangle A, B tilde, B. That's again a right triangle. So if I take the midpoint, and what's the midpoint? Midpoint is C prime, but that's not what I'm interested in. Yeah, C prime. Yeah. No, wait. Oh yeah, I'm sorry. I want to look at that different triangle. I want to look at the right triangle A, B tilde H. I'm sorry. A, B tilde H. So that's a little different. So this not the midpoint is not C prime, but it's K. Okay, so I want to look at the right triangle A, B tilde H. Midpoint is K. So if I join B tilde and K, I know that these angles, let me call them 3 and 4, these are equal. What are 3 and 4? Well, that's 3. And this is 4. We are finished in fact. So this is 4. These are the same. I know that 2 and 4 together give me 90 degrees. So 2, the angle that I call 2 and 4, they are equal to 90 degrees. Because it's a right triangle. So it means that, but 3 is equal to 4, 1 is equal to 2, so it means that 3 plus 1 is also 90 degrees. So you have actually shown that. So this was the difficult piece. 3 plus 1 is in fact 90 degrees. So you are finished. So in my list, I've got also B tilde. Check that, I think I don't need to repeat the same proof for C tilde. It's exactly the same. So there we go. So the 3 feet of the perpendiculars, 3 midpoints of 3 sides, and 3 midpoints of the line segments joining the orthocenter to the 3 vertices. These 9 points, they all lie on a circle. Do they of course, I've been careful in my drawing, but you know, I'm not a great draftsman. But you can, I think they look nice. Yeah. How about that? Roughly, the thing works. So if you repeat the same thing with GeoGebra, it gives you wonderful results. So that's okay. That's a truly marvelous thing to happen. So you have 9 points. They all lie on that line. Okay. So. And why is okay? So where is the center of this? Where is the center of this circle? Where is the center of this circle? Well, it should be, as I say, it should be midpoint of OH. And why is that? Well, that's not too difficult to see. You see, that's A tilde, that's A tilde. So let me draw this line segment. That's A tilde, and that's A prime. I remember, this is the foot of the altitude through A. This is the midpoint of BC. So if I erect a perpendicular somewhere, I shall get H. Okay? If I erect a perpendicular here, somewhere I shall get L. Okay? And I know that the center of the 9-point circle must lie on the perpendicular bisector of the line segment A tilde, A prime, A tilde. So it will be somewhere on this line perpendicular bisector. So somewhere on this perpendicular bisector. And of course, that perpendicular bisector will go through the very midpoint of OH. But you see, what you have done with A prime, A tilde prime, you can repeat with B prime, B tilde prime. And that will again go through the midpoint of OH. Now that's the extraordinary thing about the geometry of the triangle. You see, O and H are remarkable points. They've got no spatial relationship with any of the vertices. They belong to the triangle. Okay? So you know that if you draw the so perhaps you have that somewhere, I don't know. So something like this must happen. B tilde, B prime. So this will be the exact midpoint of the thing. Okay, so there we are. That's rather nice. That's rather nice. Okay, so that's the 9-point circle. That's the 9-point circle. I would like to leave this as an interesting exercise to you. So I would like to. This is actually I don't want to do it right now. So a very small homework. Left to the student. Left to the student. The radius of the 9-point circle is R over 2. So in fact, it turns out, and I'll leave this to you. Okay? If you can't do it, I will do it in my next lecture. Don't you worry. The radius of the 9-point circle is in fact half the circle radius. So I will. Well, this is a topic. This is a topic I shall revisit in a spectacular fashion towards the end of the term. Okay? I will give you something that will truly knock you out. You see, it's extraordinary. That's the nature of mathematics. You can notice something. You discover a theorem. Okay? And then it's possible to go to go a long way in some direction and to discover other things. And then sometimes it happens that you come back to a vantage point, to a point where you can have another look at the same theorem. And the theorem looks even more natural and more transparent. That's what will happen with this 9-point circle. At the end of the term, I will show this 9-point circle from a different angle. And for that treatment, it will be important that you know that this 9-point circle has radius half the circle radius. So, okay, so let me finish this subject. In fact, you see, of course, I don't want to draw it, but if you draw the circumcircle, so the 9-point circle is in fact in many ways half the circle radius. So it is something like the circle radius, but it has been reduced by factor at half. That's a topic, and I shall come back to it. Right, that's towards the end of the term. Right, so that's it. These are the 3 points, the 3 remarkable. So I'm left. So there is still the 4th remarkable point left, and I've got about 4 of an hour's time, and that will suit me perfectly. So what's the 4th point? Okay, so we have got O, the circumcenter, H, the orthocenter, and G, the centroid. The 3 remarkable points are there, and there's a 4th. That's a classical point, and once again, it's a point which was known to almost all civilizations. It is so there is going to be a 4th point. There is, however, I mean, there's a reason why I have left it to the end. This point is actually, how should I express it? Perhaps you will best understand when I've finished my explanation. But let me tell you beforehand that it's, these points are lone words. Okay, they lone ranges. They are alone. Circumcenter is alone. Orthocenter is alone. Centroid is alone. But this 4th point is, you have got these mafia bosses who are never alone. Okay, so the mafia boss goes and 3 shady characters follow him always. He has always his associates around. Now this 4th point is a point that goes nowhere alone. He's got always the 3 associates. So in a sense, it's not a single point. Let me explain. Okay, now I would like to take my time with this configuration, which is rather difficult. Let me start with 2 circles. Actually, I'm not interested in circles, but let me start with 2 circles, because as I said, it's a rather difficult thing to get right. Okay, and let the second circle be something like this, a little bigger. Okay, so I mean, although I shall be very careful, I can still get it. Okay, and I would like to draw 2 external common tangents of these 2 circles. It's very difficult to get right, so please accept my apologies beforehand in advance if I don't get them right, but I shall do my best. Okay, right, and then, okay, so the common tangent lines like this. Okay, external, and there is one internal common tangent which I would like to bring to your attention. Okay, right. Actually, what I wanted to do was not to draw these circles, but I would like to talk about the triangle itself. So let's say, take a triangle A, B, C like this. Okay. So let me get rid of these circles. And if you take the internal bisector of the angle at A, okay, that internal bisector consists of points which are equidistant to 2 sides. And if you take the internal bisector at B, well, that will also consist of points which are equidistant to 2 sides. I will talk about this. What is internal bisector, what is external bisector, but bear with me. I mean, as if you are in an elementary school. And it's optically obvious, internal, external. So these will intersect in a point, okay? And that point will be of necessity equidistant to not only these two sides, but also to these two sides, so to all three sides. So it means that if you draw perpendiculars from this point on the three sides, then these perpendiculars will have the same length. So that means that if you apply the points of your compass to this point, and if you apply the writing point to the foot of the perpendicular, which I dropped from this on one of the sides, any of the sides, it doesn't matter. If you draw the circle, then this circle will be actually tangent to all three sides. Okay? Right. So it will be a circle which will touch three sides. So let me write down the points of contact. Okay. So points of contact I shall call S, T, U. These are not traditional, these are just my choice. And the center of the circle is called I. Okay, so this is in fact my fourth remarkable point. It's called the in-center. It's referred to as the in-center. And this circle is called the in-circle. In-circle, related is the in-circle. Okay. Okay. And the radius will be usually denoted by small r, which is referred to as in radius, surprisingly. Surprise. Okay, so it's easy piece of terminology. Right. So, okay, so that's the in-center. If you take the internal bisector at A, so that's the straight line that joins A and I, and if you extend it, so all the points are equidistant to the two legs of this angle at A, very fine. If you take the external bisector at B, okay, so these will intersect in a point, and that point, so if you take the external bisector at B, then every point on it will be equidistant to the line BC and line AB extended. I will come back to this. This is optically quite obvious, but something that has to be made a little bit more precise. So that means, of course, that the point in which these two lines intersect will be equidistant to BC, AB in extension, and of course AC extended. So it means that if you take C and join it to this point, this must be also the external bisector, angle bisector at A. Okay, so that means if you draw a perpendicular from this point onto the three sides, okay, so like this, and like this, and like this, if you draw these three perpendiculars, you will get three equal lines. So these three lines are in fact equal in length. Well, that means, just as in this case, so let's call this point I sub A. Okay? Now, what happens is, of course, once again, if you take your compass and if you put the points at this point, if you apply the point at this point, and then put the writing point to this point, and if you complete it, it will pass through all these points, and so you will obtain a circle which is actually tangent to BC, tangent to AB, and CA extended. Okay, so you will get something like this. Now, this is the best I can do. You know, it's very difficult to draw on the blackboard. I think we should look a little bit better if you have notebooks. So this circle will touch, so to speak. So this is a circle which touches three sides. but from outside. So let me, okay, so the points of tangency, let me give them names. So let me call this point of tangency to the side BC is touched by this circle at SA, sub A. This is U, so let this be UA. And this is T, and let this be TA. Okay? To check that, I'm not interested in this. I'm not immediately interested in this as TU, as ATU, but I'm interested in IA. So this point, in fact, comes along, the point in center, comes along also with IA, which is called the X center. And, well, of course, I think it would be insulting your intelligence if I say that whatever I have done in this part of the world by taking the internal bisector at A and the external bisector at remaining two angles, I can repeat this process here. So I can take, for instance, the internal bisector of B and the external bisector of C here. So I can obtain a circle here and a circle here. And I can, of course, obtain X centers, IA, IB, IC, three of them. So I don't know, the terminology is not quite clear. So you can refer to this, for instance, X center opposite the vertex A. And of course, you can have the X circle. So this thing is called X circle, and its radius. Okay, so let me be a little bit more careful. So this radius and this radius. Okay, so this is going to be, this is called, referred to RA. This is the X radius. And if you want to be quite precise, you must say that this is the X radius opposite A. So there we are. So let me get rid of all this. And we're home free. Okay. Now let me make these dotted lines. Let me get rid of these. Okay, so that's the thing. So this is the in-center. Is your fourth remarkable point, yet you know it's never alone. It's just like a careful mafia boss who always walks around with his three associates. You know, whenever I give you a theorem about I, there will be versions of the theorem involving the IA, IB, IC. Okay. So that's the thing. But there is one last thing. Okay, so how much time do I have left? I think I've got just enough time to tell you something very simple. Yes, indeed, very simple. It is the following. It is a well-known procedure that there are some very interesting metric properties. Okay, so for instance, okay. So by the way, I think it's obvious, isn't it? If I take a circle. And if I take a point outside and draw tangent lines, then the line segment that's arise with its endpoint at the point and at the point of tangency, these two things are equal in length, aren't they? So this is equal to this in length. So I'm not going into that, that's very easy. So it means that AU, if I call it X, AT is also X in length. So if I call BU Y, so BS is also Y, and CT, if I call it Z, then CS must be Z2. So this is Z, which is fine, but not only that, you got also the following situation. You see, so what else do I know? I know, yeah. Okay, so what I know are the following. I know that if I take Y and Z, they add up to give the length of BC, which is A. If I add up, okay, so let me proceed cyclically, Z plus X, that will give me B. If I add up X and Y, that will give me C. So if I add them all together, I shall obtain 2 times x plus y plus z. If I divide both sides by 2, I will obtain x plus y plus z equal to, well, a quantity which is traditionally referred to as the semiperimeter. The semiperimeter. Okay, so this is actually all familiar to you. Should be semiperimeter. This is in fact nothing but the perimeter of the triangle divided by 2. Okay, so that is it. On the other hand, finally, now let's observe finally that the length AU and the length ATA, AUA, and ATA, they must be the same. Well, so on the other hand, you see the length BUA and BSA are the same, and of course the length CSA and CTA are the same. So these tell us that in fact, this part, this object must be, so these 3 must add up to x plus y plus z, so this is z, and this must be y. So you've got this very curious configuration, and one thing is to be noticed. Okay, so by the way, since the sum of x plus y plus z is s, and the sum of y plus z is a, you come to the conclusion that x is, of course, s minus a. So you can derive similar formulae, s minus b. These are very nice, and these are quite well known, but I'm repeating them for the sake of completeness. I would like to finish now by just observing one very important thing. I want to direct your attention to this line segment BC. BC. The point S is here, and this length is S minus B. The point SA is here, and this length is S minus C, and this length is, this whole thing is A. So this thing is this. Okay. So yeah. This is y, and this is y, and this is y. So they must be. So these 2 pieces are equal. Okay. So CSA. Okay. This piece is y. This piece is y. This piece is y. So it means that the point of tangency of the internal incircle and the point of tangency of the x circle are points on the line segment BC which are symmetrically situated with respect to the very midpoint. Okay, this is important. This is important. They are symmetrically situated with respect to the midpoint of the line segment. Now this is a theme which will occur and occur and recur and recur. Okay, so that's what I would like to start.